Okay, today we are going to talk about sinusoidal steady state power calculations. This is the last chapter that we wanted to cover. Okay, so first of all, I want to congratulate you for sticking with me through this busy, extremely short summer semester. It has been incredible journey. It's a pleasure. It has been a pleasure for me to interact with you. And I'm actually impressed with the overall class performance on the quizzes, on the homeworks, and also with the discussion in the class. Okay, I'll be seeing some of you. Okay, I'll be seeing some of you in Triple 108. Okay, sorry. My bad, my bad. Where did you guys lose me? Where did I lose you guys? Did you see me right on this PowerPoint slides, or did you lose me on the Moodle web page? On the web page. Okay, okay. I see. So let's go back. Here is what we are going to look at, Chapter 10, Sinusoidal Steady-State Power Calculations, okay, in which the voltage, okay, and the current, both of these are sinusoids, okay. Most of the, nearly just about all the power, all the electric energy that is supplied through utilities to our homes, to our offices, is all in the form of sinusoidal voltages and currents. Okay, so the voltage is a sinusoid, current is also a sinusoid. Okay, when you go to do the power calculations, you know power is V times I. So when you do multiply the voltage times the current sinusoids, owing to the fact that both of these are sinusoids and um, they're easy to manipulate, play around with using trigonometric identities, you'll end up, when you multiply V and I in the trigonometric form, you'll end up with three terms. Okay, so that's the idea. Each term has a significant, has an intuition, and has a specific form that we are interested in. Okay, so this chapter is all about sinusoid power, which is the product of sinusoid voltage and sinusoidal current. Okay, so we are going to look at average power, reactive power, complex power, and apparent power. Okay, so like I mentioned, the product of these two provides us with three terms. Okay, let's see. Let's start by looking at the instantaneous power at any given instant of time. Okay, if you remember, the power is always calculated in accordance with the passive sign convention. Okay, when the current, when the direction of the current, okay, when the direction of current is from the positive to negative along the voltage drop, okay, when the direction of the current is along the voltage drop from positive to negative, okay, then we call the power is positive. Okay, if that's the idea, passive sign convention. Okay, so when I have a voltage source and a current source, the product of these two gives me the instantaneous power, which is the power at any given moment. Okay, so this chapter there are going to be a lot of trigonometric manipulations, simple manipulations using the um, trigonometric identities that we are very familiar with. I leave that as an exercise to you. These are very simple, straightforward. What I will do is I'm going to talk about the final result, okay? The intuition that the final result provides us, okay? So with that as the understanding, let's continue here. The premise, with that as the premise. So we are looking at the product of power, which is a sinusoid, and current, which is also a sinusoid, okay? So notice that theta V is the phase angle associated with voltage. Theta I is the phase angle associated with current. Okay. So again, if you remember, offset at zero time, that represents the phase. Okay. If you remember, that's the idea of phase. The phase represents the offset in zero time. Okay. Now, see, when you do this multiplication, Vm cos omega t plus theta v times Im cosine omega t plus theta I. Okay, typically power engineers prefer to write the current as the zero angle. And then, so we can slightly simplify the last equation to incorporate. What all we are doing is shifting both of these waves. We're shifting both of these waves. The product is still going to be the same by the theta I. Now we can do the product of these two terms. Okay, when we do the product of these two terms using the simple trigonometric identity here, the final result is going to look like this. Okay, so there is Vm times Im that is multiplying all of the terms within the bracket. Okay, the Vm times Im is multiplying all the terms within the bracket. Okay, now there is a cosine so there's a cosine theta v minus theta I term, and there's a 2 omega t theta v plus theta I term. Okay, let's examine these two terms. One term is this guy, the other term is this guy. Okay, but simply the product Vm Im times the two cosines. Okay, when you simplify that, look at this term, the blue one on the left. It is divide of omega t. There is no omega t term here. So this is not frequency dependent. This is constant. Remember, theta v is a constant phase value. Theta I is a constant phase value. If theta v minus theta I equals to 0 degrees, if they're in phase, all of this term goes to 1. Okay, and then you're simply left with Vm Im over 2. But regardless, even if they are 0 degrees or not, regardless, the idea is that there is no omega term. There is no frequency component in here. So we like to call this as the DC component, okay? And then it's not time varying. In contrast, this guy has an omega, 2 omega term actually, okay? If the sine wave input voltage is like so, and the output and the input current is like so, okay? It seems the frequency of the power is twice. So the power has a frequency of 2 omega as opposed to the voltage itself, which was omega, 1 omega, and the current itself. Both of the current and voltage had a frequency of omega, while power seems to have a frequency of 2 omega. That's something that we want to notice. Okay, two terms here. There's a term that doesn't have a frequency component, and there's a term that has 2 omega t component. Okay, what we can do is to further simplify this. These two terms that you see here, especially the purple one, the blue one is still the same. Remember, the blue one is Vm Im over 2 cos omega theta v minus theta I. So this is the constant term, time invariant one. The DC one, there is no frequency component in here. That's as it is. That didn't change. That didn't change at all. The only thing that changed is this guy, the one shown in purple. Okay, the one with 2 omega t. All I have done is to write that as a cosine term minus a sine term. Okay, all I have done is cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. Okay, so that sum over here, that term within the brackets here can be expanded. Okay, that term can be expanded to incorporate a sine and cosine term. Okay, so that's the idea. There is Vm Im over 2 That seems to be present in all the three terms, Vm, Im over 2. Okay, that seems to be the common term in all the three, um, three components. Then there is a cosine. So this guy is constant as well. Theta v minus theta I, as long as theta v and theta I are not changing. This guy is not changing with time. So there is a cosine 2 omega t, and there's a sine 2 omega t term. Okay. So the idea is that here is three terms. Okay, when you multiply v of t in a cosine form and I of t in a cosine form to look at power, I ended up with the power that had three terms in it. It's a constant DC value that's not changing. We like to call this as the average power. Then there is a cosine term that is varying at 2 omega t. And then there's a sine term that is varying at 2 omega t as well. So this sinusoid, this sine term, we call this as reactive power. So if you're asked to find the reactive power, all you have to do is to calculate Vm, Im over 2 times sine theta v minus theta I times sine 2 omega t. Okay, so that's all there is to reactive power. So this component, there are three terms to the power equation. Okay, the third term, which is a sine term, that represents the reactive power. Okay, so we already looked at the reactive power and the average power. Okay, the constant non-changing term is called the average power. Okay, this guy, let's see, this guy that has a sinusoid power is called the reactive term. Okay, in this case, Q is going to be Vm Im over 2 times sine theta v minus theta I. Okay, that's the reactive component. So it's simply a matter of um, expressing these terms separately. And of course, there is a cosine component as well. That's this guy. Okay, there's three terms that we looked at for the power product. Okay, average power is defined as the average power that is delivered to a circuit. The reactive power, Q, is defined as the reactive power that is temporarily stored by the circuit. So if you have components like inductors, capacitors that can store electric energy, okay, inductors store electrical energy in the form of magnetic field. Capacitors store electrical energy in the form of charge, okay? So if there are some reactive components like inductors or capacitances, then Q is some temporary storage of charge, okay? Temporary storage of electrical energy power. Okay, so let's look at the power for each of the three devices that we know: resistor, inductor, and capacitor. Okay, we know for a resistor, the voltage and the current are in phase. So theta V is the phase of the voltage, theta I is the phase of the current. Okay, so what we are going to do is to use this template, not this guy, this template. Okay, and plug in the relative values of theta V and theta I. Okay, when we do that, we know theta V equals to theta I in a resistance. Okay, and of course, cosine 0 is 1, sine 0 is 0. So what happens is the last term, negative Q sine, okay, omega t, 2 omega t, that goes to 0 because Q goes to 0. Remember? Let's look at Q. What is Q? Q is this guy. All of this guy is Q. Okay? Okay, but theta V minus theta I is 0 in a resistance. Therefore, all of this term is going to go to 0. So there is no reactive term. Okay? There is no reactive term in the resistance, in the power equation for resistance. Okay, let's see. In the power equation for resistance, the reactive term all goes to 0. So there is this cosine term, and then there is the average term. So for a resistor, okay, notice that the sign is positive, meaning that the resistor can only absorb power. Okay, this is the instantaneous power for the resistance. Okay, let's see what happens for an inductor. Okay, for an inductor, and I mentioned in the last class that the way you want to remember is Eli, the Iceman. Okay, voltage leads current in an inductor. Okay, so that's the idea. So theta V minus theta I equals to 90 degrees. Okay, or theta I or theta V minus theta I equals to 90 degrees. That's the idea of voltage leading the current in an inductor. So we can plug this number in place of the theta V minus theta I terms. Okay, cosine 90 is 0, sine 90 is 1. When we plug it back in, all we will see is that the average power. So two of the three terms. So you plug in theta V minus theta I equals to 90 in the equation here. When you plug that in, okay, this term goes to 0 because theta V minus theta I, cosine of that, okay, see, cosine of theta V minus theta I is 0, so this term goes to 0. Similarly, there is a cosine theta V minus theta I term in here, so when theta V minus theta I is 90, cosine of 90 is 0, so all of this term goes away. So you're only left with the reactive power for an inductor. Okay, let's see. So for an inductor, okay, for an inductor, you're only left with the reactive term, negative Q sine 2 omega t. This reactive power, we like to call its units in volt ampere reactive. The inductors, and notice that the sign here is negative. There is a negative sign, meaning that inductors demand or absorb magnetizing voltage ampere reactives. Okay, inductors absorb magnetizing VARs. Okay, so that's for the inductor. For the resistance, we had just the average and the cosine with a positive sign, meaning that the resistor absorbs. Okay, now let's see the capacitor. Okay, the capacitor circuit. If you go back to Eli the Iceman, mnemonic, the current leads the voltage in a capacitance. Okay, so the current leads the voltage by 90 degrees. Okay, so the theta I is greater. Okay, so theta V minus theta I is going to be negative 90 degrees, owing to the fact that current leads the voltage by 90 degrees. Okay, then we can substitute, we can plug that in to the above equation. Cos negative 90 is 0, sine negative 90 is negative 1. So what we have is the average power in a purely capacitive circuit is 0, just as the average power in a purely inductive circuit is 0. Okay, average power in a purely inductive circuit is 0. Average power in a purely capacitive circuit is 0. Okay, and what is important is the power is still Q times sine 2 omega t. That's exactly the same as it was for the inductor, Q sine 2 omega t, except that the sign here is positive. Okay, capacitors can actually deliver or furnish magnetizing voltage ampere reactive VAR. Okay. Now that's the idea of capacitors power. Okay, the power in resistors had some P average plus P average times cosine 2 omega t term. Okay, power in inductance had negative Q sine 2 omega t, something in that along those lines. Power in a capacitance has positive Q sine 2 omega t. Okay, so that's the overall summary that you want to understand from the discussion here. The instantaneous power is that guy. Okay, we can define a new term here, power angle, as the phase angle between the voltage and current. Okay, earlier we saw different power phase angles, theta V minus theta I equals to 0 for a resistance, theta V minus theta I equals to 90 degrees for an inductor. Okay, theta V minus theta I equals to negative 90 degrees for a cap. Okay, so there can be any number of number of values for theta V minus theta I. So it doesn't have to be the exact same numbers. Okay, 0, 90, or negative 90. There can be any number of different values. Now, we also know that cosine positive theta equals to cosine negative theta. Okay, cos negative 45 equals to cosine of 45 degrees. Cosine of negative theta is cosine of theta. Okay, we need to add the term lagging to the power factor for an inductive load where the current lags the voltage in order to clearly specify. Okay, in order to clearly specify whether sometimes what happens is the cosine term can camouflage um, the information about which one is leading and which one is lagging. So in order to be absolutely certain, what we do is we add the terms lagging and leading. Okay, so when we say leading, all we mean is the current is leading. So power engineers like to think of everything in reference to a current. So when we say leading, it means the current is leading. When we say lagging, in this context, it means the current lags the voltage. Okay, the sinusoidal reactive factor is defined as this guy. Okay, so cosine of theta V minus theta I is defined as the power factor, while the reactive factor is defined as sine theta v minus theta I, all based on the idea that the difference theta v minus theta I is of importance to me. Okay, if you do the cosine of it, you call it the power factor. If you do the sine of it, you call the reactive factor. Okay, sometimes because the power factor, there's no sine to it. Okay, cosine, the information about whether the angle here is positive or negative is camouflaged by the cosine function. So we add the terms leading and lagging. Okay. Here is an example. So voltage is given. Okay. Current is given. We are asked to find out the power factor at the terminals of this circuit. Okay. We must first put the given voltage and current into a common form, or phasors will be meaningless. So meaning that we want to convert this guy to cosine as well. We want to keep just about everything in the same cosine form. So here is my effort to convert the current in sine form into cosine form. Okay, I simply subtract a phase of 90 degrees and it gives me, so the idea is that that's your sine. Okay, your cosine is nothing but, I didn't want to do that. I wanted to do this. Okay. That's your cosine. Okay, one is cosine. The other is a sine. Okay. You know that cosine of omega t minus 15 degrees minus 90 degrees, they're just time shifted values of one another. Okay, so sine and cosine, that's a trigonometric identity that we are familiar with. Okay, so using that identity, I have converted the sine omega t minus 15 into cosine omega t minus 15 minus 90. Okay, so now what I can do is notice that this guy is in cosine and the voltage is in cosine. Now I can convert them to phasor or do whatever I want to do. So the power factor I'm interested in calculating is cosine of theta v minus theta I. Okay, theta v minus theta I. The theta v is this guy, 15 degrees. That's theta v. Theta I is this guy. That's this guy. Okay, so I have a cosine of 120 degrees. Be careful not to forget the additional negative sign, theta v minus theta I. Okay, theta I is negative 105, and you plug that in here. Theta v is 15. Theta v minus theta I gives you cosine of 120. Okay, now you have a negative 0.5. Okay, cosine of 120 degrees is negative 0.5, and then the current is lagging. Okay, see, the theta v is 15 degrees, theta I is negative 105 degrees. Okay, the theta phase angle for current is lower than the phase angle for voltage. So theta v minus theta I, okay, is positive. Therefore, I call it lag. Okay, so theta v minus theta I is positive, hence the term lag. Okay, and then that's the first part. We can calculate the average power at the terminals of this network. The average power, if you remember, is simply Vm Im over 2 cos theta v minus theta I. There is no omega term. Remember, that's the idea. of average power. Okay, you plug in the numbers, you get a negative 100 watts. Okay, the negative term signifies that the circuit is delivering power to load. Okay, it's delivering power to load. Questions, please. In the chat. Okay, so this device is delivering power. The circuit is delivering power owing to the fact, signified by the fact that the power, average power is negative 100 watt. Okay, so all I'm doing so far is simply multiply V of t sinusoid by I of t. You manipulate that, you get three terms. Okay, one term is called the reactive term, which had a sinusoid about it, and then there is a cosine. Okay, term, and then there's a average power term. Okay, so there are three different terms. Okay, when you do the multiplication, okay, one of them is called the reactive term, the other is called the average term, so on and so forth. Okay, so here is another problem. Okay, it's the same problem, it's a continuation of the same problem. Okay, now how do we calculate the reactive power? Okay, this term, Q term, okay, multiplied by sine 2 omega t, that gives us the reactive power. Okay, so we can calculate the term Q over here. That comes out to be whatever it comes out to be. Okay, multiplied by sine 2 omega t. Okay, sine 2 omega t. That gives us the reactive term. But here we are simply multiplying Vm Im over 2 sine theta V minus theta I. Okay, this 120 is theta V minus theta I. We are just looking at the Q term when we want to calculate the Q term. Okay, we can get a value for that. Positive 173.2 voltage ampere reactive. We see that the network is absorbing. Okay, the network is absorbing power, which is an inductive network, as indicated by the lagging power factor. If you look at the power factor is lagging, meaning that the current is lagging or the voltage is leading. There's only in the resistance, that's not possible. In the capacitance, voltage is lagging, but in an inductor, it's the current that is lagging. Okay, so when I like to mention everything in reference to the current in this context, right? So when I say lagging, the current is lagging, meaning the voltage is leading, and that signifies an inductor, and that's borne out in the fact that the reactive power is positive. Okay, when the reactive power is positive, the power is absorbed. Okay, hence it's an inductor. Okay, let's see what else. Okay, now we looked at the instantaneous power. With its three components, P average plus the P average times cosine 2 omega t plus P average, or it's not the P average, it's the Q times sine 2 omega t. Okay, so we calculated Q using the power factor in a average. All of these can be calculated. We calculated the power factor reactive power factor, so on and so forth. All of these are based on the idea that you're simply multiplying two sinusoids, okay, and then massaging the equations. That's all there is to this part, okay. Now let's look at the RMS value, okay, the RMS value and power calculations in the RMS value, okay. The average of a function f of x is given by integral f of x dx, okay. So integral is nothing but, intuitively thinking about it, it's a continuous sum, okay, or area under the curve, so on and so forth. If I have a function, I add up, make a continuous sum of all the values of the function and divide it by the range, okay, divided by the number of terms, okay, which is the terms here, t over here, that's the difference. Then I have an average. That's what is the definition of an average, okay. So the root mean squared of a function is defined as that average of the square root of the function and taking an under root, taking a square root later on. So the idea is for functions that are both positive and negative, that have both the positive and negative values equally distributed, if you take the average, that comes out to be 0. So what we like to do is to square the function first, then take the average, okay, and then do the integral of it, okay. So that's the idea. We do the root mean squared calculations. When we do the root mean squared calculation, okay, we see that the power average is VRMS squared over R. Okay, this simply is for a voltage of Vm cos omega t plus theta V. Okay, if we do the integral of the square root of that function, okay, and remember that this voltage is applied across the resistance, okay, across the resistance, okay. The power average is VRMS over R, or it can also be expressed as I squared RMS, V squared RMS by R, or I squared RMS by R, okay. So these are the expressions for power in terms of the voltage, or if I were to use a current source, that would be the current I squared R, okay. Now we can do this arithmetic, we can do this massaging the equation and find that VRMS is Vm over square root of 2. Remember Vm, okay, Vm cos omega t plus theta V, okay, or sine omega t plus theta V, okay. If the amplitude is Vm, if the maximum value, peak value is Vm, then the RMS value is simply Vm over square root of 2. And this is a relation that you should remember for the rest of your life. The RMS value of a sinusoid signal, whether it is sine or cosine, is Vm, the amplitude, over square root of 2. Okay, that's the RMS value of voltage. Okay, the RMS value is often called the effective value. RMS value is called the effective value. So the average permanent power in terms of the effective value can be shown that P average is VRMS times IRMS times cos of the power factor, cosine power factor, theta V minus theta I. The reactive power can also be stated in terms of the effective value. So there is a, remember this, the average power, And then there is the reactive power. The reactive power, the term that has the sinusoid associated with it, is V effective or VRMS, I effective, IRMS. So when I say I effective, all you have to realize is this guy, VRMS, is the same as V effective. Okay, this guy, I effective, is the same as IRMS. Okay, so IRMS is the same as I effective. Okay, and then of course there is the sinusoid term. Okay, RMS value is often called the effective value. So I can calculate the reactive power in terms of the effective or RMS values. Okay, so here is an example. Given the expression for voltage, notice that the phase angle is 0 over here, and the value of the resistance is given. We are expected to find the average power delivered to the resistance. Okay, the voltage in terms of RMS. So what we are going to do, the first things first, is I'm going to express VRMS as VM over square root of 2. VM is 625, or the peak value is 625. I'm interested in the average power. Okay, so using that, I have a value for VRMS. Now the average power that is observed is simply VRMS squared by R. See, the average power is V squared by R. When you're using this V squared by R or I squared R formulas for power, you want to remember that you should not use the instantaneous power. Rather, you should use the RMS values. Okay, that's not the instantaneous voltage or current values. Okay, that's all there is to it. So I calculated VRMS, V squared RMS by R gives me the power. 3.90625 watts. That's a whole lot of wattage. Okay, that's a lot of power. Okay, the power absorbed by the 50 ohm resistance is that kind. Okay, and then there is also the idea of complex power, simply the sum of P and Q. Okay, complex power is the sum of the real and the reactive power. Okay, and here theta is the power factor angle, theta V minus theta I. When you express it in terms of the polar form, S angle theta, that can be S cos theta plus J sine theta. Okay, S times cos theta is defined as P, the real part. Okay, Q is defined as the imaginary part, S times J sine theta. Okay, the real part and the imaginary part. Now let's see, the apparent power, that's simply the magnitude. Okay, magnitude of P squared plus Q squared under root, that's defined as the average power. Okay, so it's just a matter of becoming familiar with these terms. One of them is called the real part, one of them is called the imaginary part, and for obvious reasons, no prizes for guessing as to why they're given that name. Okay, now the last definition leads to two very useful relations, where P is the real part. Okay, the real part can be calculated from the angle here. If you know the angle, power factor angle, theta V minus theta I, you can calculate the real power. You can also calculate the imaginary part of the power, and then you can add the two to give us the complex complex power. Okay, Very simple idea. Okay, an electrical load operates. Here is an example. Electrical load operates at 240 V RMS, absorbs an average power of 8 kilo ohms with a lagging power factor of 0.8. You see, with a lagging power factor of 0.8, meaning that theta V minus theta I is positive. Okay, theta V greater than theta I. Okay, that's the idea of lagging. Okay, calculate the complex power of the load. So we are asked to find out the complex power of the load. So we are expected to find P plus J times Q. Okay, that is what we are after. As you will see, the final result is P plus J times Q. Okay, so we have to individually find the P value and individually find the Q value. Okay, and what's the value of P? Remember, P, it's a lagging power factor, which means the current lags the voltage, or an inductive load. It's an inductive load. Like I mentioned earlier, theta V minus theta I is positive. Okay, so we can do P is, in order to find the, in order to find P, we do modulus of S cos theta. Okay, and modulus of S comes out to be P over cos theta. P is given to be 8 kilovolts. 8 kilovolts, that's the average power, right? The average power is given to be 8 kilovolts by 0.8. So the magnitude of S is 10 kilovolt ampere. Okay? 10 kilovolt ampere. So we found the value of magnitude of S. Now the power factor angle and the sine theta can also be found, because cos of this angle is given to be 0.8. The angle can be cosine inverse of 0.8, right? So the power factor is given to be 0.8, meaning that the theta V minus theta I is 36.87 degrees. So if I evaluate sine theta for it, it comes out to be 0.6. Why do I need to do that? I'm interested in calculating Q, which has a sinusoid term, right? Now the reactive power can be calculated from using the magnitude that we just found out times the sinusoid, which comes out to be 6 kilovolt ampere. Okay, so all we have done is to simply use the two pieces of information. This means cos theta V minus theta I, that is given to be 0.8. Okay, similarly, this is given the average power, P average is given to be 8 kilowatts. Okay, let me go back. Okay, so the real part, okay, which is P of P magnitude of S times cos theta. Okay, so P has been given and cos theta has been given. So from that I find out the value of S. So once I have the value of S, okay, once I have the value of S and I have the value of theta from here, I should be able to calculate sine theta and then calculate Q. Okay, so using these different techniques, I'm able to calculate. So P has already been given to be 8. Okay, Q we found out to be J6. And thank you for the help along the way about the inductive power and then inductive load. Okay, and the power factor uh, lagging. Okay, so that's the idea. So if this were a leading power factor, then what we would do is instead of taking a 36.87 as the value, we take negative 36.87. Okay, the negative 36.87. Okay, and that comes out to be a negative JQ. Okay, That's all there is to it. So let's see if we can go to power calculations really quickly. Power is Vm Im over 2 times P is cos theta V minus theta I. The Q is Vm Im over 2 times sine theta V minus theta I. So there are two components to the power, complex power, right? P plus J times Q. Okay, there are two components to it. We can see the real part and the imaginary part. Okay, the real part and the imaginary part. Both of these depend on the power factor angle, theta V minus theta I. Okay, and of course the peak values Vm and Im. Okay, so what we are doing is simply manipulating the complex number, using Euler's identity, and we are expressing the last term as V effective times the complex conjugate of I effective. Okay, so the power can be expressed as the effective voltage times the complex conjugate of the effective current. Okay, in terms of the maximum voltage Vm and Im, we can write power S is 1/2. Remember, V effective was Vm over square root of 2. I effective was Im over square root of 2. And there's no surprise if you remember that you're multiplying this square root of 2 and this square root of 2 together. There's no surprise that the denominator there has a 1/2 term or a 2 term in the denominator. Okay, so the maximum Vm, so this guy is actually Vm and Im expressed in terms of the maximum power, and these are expressed in terms of the effective voltages or the RMS voltages. Okay, as long as we carefully write the complex form of the voltage and current, we can write V effective is Z times I effective. Okay, where Z is R plus the resistive component plus the uh, reactive component. Okay, the powers can then be expressed in terms of I squared R, I squared Z, V squared by Z, and I squared um, X, so on and so forth. Okay, the reactive component can be expressed in terms of X. Okay, the power can be expressed, the average power can be expressed in terms of R. Okay, and then of course the complex power itself can be expressed in terms of Z. I squared Z or V squared. So remember, they do not deviate a whole lot from this idea, I squared R, V squared by R. Okay, the power, expression for power. And you see that I squared times multiplied by R, I squared times multiplied by the complex impedance, so on and so forth. Okay, so here is an example. The voltage is given, here the current is given, similar to the last problem. This appears to be the exact same problem as we saw previously. Maybe not. No, doesn't matter. The idea is the phasor form of the inputs. Okay, V is 100 angle 15. The current is this guy. Okay, so that's the current is 4 angle negative 5. So the complex conjugate of this is 4 angle positive 105. Remember, we can use the complex conjugate to calculate the power, complex power. Okay, so we can use the complex conjugate to calculate the power 1/2 V times I. Okay, remember we had 1 times V times I, I complex conjugate. Okay, when we do that, we can get the um, power, complex power 1/2, 100 angle 15, 4 angle 105. So the multiplication of phasors is easy. I simply multiply 104 and 1/2 to get 200, and then add the angles here. Okay, 105 and 15 gives me 120. Okay, and when I convert it to complex number, 100 plus J 173.2 voltage amperes. Okay, that's the idea of calculating the complex power. Okay, questions, please. So all there is here is to understand the definitions of the different terms. Okay, once you know these definitions.
Professor, one question. So basically, on the homework, it cuts off at 10.3. Would we have to understand all the definitions for the test, or would you recommend it just for practice for the future?
Well, I think for the final exam, it's important to go all the way up to 10.5 and even take a quick look at 10.6 as well. Okay, but for the homework, maybe you can stop at 10.3, but practice 10 up to 10.5 as well for the exam. Other questions, please. So it's okay with me if you want to have a cheat sheet on the exam, one sheet of paper on which you have written down just about anything that you want to do. As a matter of fact, I encourage you to do that. Okay, so um, if you spend time into crafting your formula sheet, that's actually a review of one whole semester's worth of topics. And that's going to be helpful for your exam and um, for quick reference later on. Okay. Other questions, please. So why don't we stop here and then